Hi, I'm Vineet, and our work is called a Unified Deep Learning Approach for Foveated Rendering and Novel View Synthesis from Sparse RGB-D light fields. Let me give you a brief background regarding our problem statement to better understand this. Our work is focused on near-eye light field virtual reality displays. These provide a solution to the visual discomfort by effectively addressing the divergence accommodation conflict, and users can experience enhanced depth perception compared to conventional head-mounted displays. A light field scene is represented as a 4D tensor which can be visualized as a matrix of images taken from slightly shifted viewpoints. An example is shown here with 81 views in a 9 by 9 grid, compared to conventional displays where only one view needs to be rendered. This poses a computational challenge, especially when using realistic rendering techniques such as ray tracing, since the number of pixels to render can become very large. There are ways to reduce this, and one popular method is view synthesis. Here we render only a few selected views shown in blue and synthesize the rest using a suitable interpolation function. Another technique used in conventional displays is foveated rendering, which uses the fact that our eyes do not have uniform acuity throughout the field of view. This requires rendering different regions of the image at different resolutions, but this requires using a gaze tracker. Our solution seeks to combine these techniques to be used for light fields. We did not find any existing works that attempt this. Broadly, our method has two main steps: selected rendering of views and regions, and a CNN to reconstruct the full light field. The end-to-end flow is described here. First, we select a fixed set of views and render them with foveated sampling. This would be a small fraction of the total light field. Then these images are smoothed, which is used as input to our CNN, which we call FES ResUnet, which then reconstructs the full light field from limited data. Let's look into each of these steps. For each selected view, we perform log polar sampling and smoothing, which has a foveated rendering like effect. The sampling density is high near the foveal region and it quickly falls off near the periphery. We can control the sampling densities as well as the offsets by changing certain parameters. Our CNN has two main components: a resonate backbone and a unit in parallel, hence the name ResUnit. These are made up of repeating units of residual blocks in the case of the resonant backbone, which transforms the input as an identity mapping with offsets, and this efficiently models view interpolation. The downsizing and upsizing blocks of the unit results in a large receptive field, which is useful in regions where the sampling density is low. We include interleaving and deinterleaving layers to cause a small dip in quality but greatly reduce the runtime. We use a PSNR loss of both pixels and image gradients between the prediction and the targets for training. Here is some information about the data that we use. The light field images consist of 81 views in a 9 by 9 grid with 512 by 512 spatial resolution. For training, we use overlapping patches of size 128 by 128 to increase the size of our training set. For testing, we use the full 512 by 512 images. For evaluation, we estimate the retinal image and calculate the SSIM in multiple regions. We call these the fovea, P1 and P2 for periphery 1 and periphery 2 respectively. Since there is no direct comparison available, We compare to a state-of-the-art view synthesis method, deep focus. Here is a table showing the performance of our method with varying sampling rates. Our method has comparable SSIM to defocus with similar sampling, but we are able to reduce the sampling a lot and still maintain acceptable foveal qualities with scores decreasing in the periphery. This table shows a different similar trend at a different focus. Here are some qualitative results. As you can see from the SSIM error map, the error in the foveal region is low, but it increases towards the periphery. Similar results here with a different focus. Here are results on some more scenes from a different data set, and these two have good foveal quality but with varying peripheral quality, depending on the details uh, in the periphery of the scene. We compare the runtimes of our CNN to deep focus, and we find that it is slightly slower. But deep focus performs view synthesis, whereas ours does both view synthesis and foveated rendering and requires around 10 times less data. To summarize, our method requires only about 1.2% of the total light field to be rendered for acceptable quality, and this is done utilizing view synthesis and foveated rendering. In the future, we hope to optimize the CNN architecture for both speed and performance, and also explore loss functions that account for foveated rendering. We would like to thank the organizers for conducting this despite the challenges, and we would also like to thank the reviewers who have given us valuable feedback. Thank you, everyone.